Everyone, welcome to your play posit for the week. I hope you guys are all doing well. We're going to be covering 1.10 through 111 and 1.14. So go ahead and grab your notes. You're going to want to grab your notes from last class and for the play posit today. Before we get started, just a reminder, we're going to finish those notes from last class, talk about transformations, and then also how those transformations are actually related to algebra with some cool examples of that. Just a note here, on any typical week, we're only going to have one play posit and one live class. But because this week and next week are a little bit different, since we have those Virginia growth assessments, we're actually going to have two play posits this week and next week. And this is so you guys don't miss any important instruction. So I do realize since we're not having live class, it's a little bit different. So today's play posit will be the usual length, maybe like 40 minutes, 45 minutes. And then the Thursday one's going to be super short, maybe like 15, 20 minutes. And this is just so I can get you guys that important instruction that you need. And then I am so excited because the week of the 27th, we will resume our regular year schedule and I'll have one play posit for you guys on Mondays, and then I'll see you on in live class once a week. So just to finish our notes up from last class, this was an example we were going to go over. And basically, they give you a bunch of angle measures and a few different diagrams. So we can look at the first diagram, and we just want to label everything that we know. And here's the first bit of information. It tells us that angle 1 and angle 3 are congruent. So we can mark those equal. Remember, we use those markings. We don't know what they are, but we do know that they're equal. Let's keep going. Angle 2 is 84. Oh, here we go. Angle 3 is 20 degrees. So because of this important marking here, then we know immediately that angle 1 is also 20 degrees because they're congruent. Let's look at the second diagram. Angle 4 is 20 degrees. Angle 5 is 84 degrees. Angle 6 and angle 1 are congruent, right? And we know angle 1 is 20, so angle 6 is also 20, and angle 7 is 76. So in both of these, the big deal was using that angle 1 relationship between angle 3 and angle 6. So this was just some good practice with this symbol here. Remember, this means congruent, and that means that they're the same measure. We can have congruent angles, and we can also have congruent side lengths, which you'll see soon. The next thing we're going to talk about are adjacent angles. This word adjacent, you might think of next to. I know I do. If you're adjacent to someone, you're right next to someone. So adjacent angles actually share a side. That's the big deal. So we could say angle AOB, this one, is adjacent to angle BOC. See, they share this side OB. So these are adjacent. Let's look at a pair that's not adjacent in this picture. I bet you can find some. What about angle AOB and angle COD? That's this sort of top angle and this bottom one. They share a vertex. They don't share a side, so they are not adjacent. And adjacent angles are going to be pretty important when we talk about linear pairs, which we'll see here in a minute. Complementary and supplementary are topics you guys have dealt with before. Complementary angles add up to 90 degrees, and supplementary angles add up to 180 degrees. You're going to think I'm so silly, but one way to remember this is supplementary starts with an S, right? Look how we can turn this S into an 8 for 180. Complementary starts with a C and an O. Look how we can turn the C into a 9 for 90 degrees. I know that's silly, but sometimes visual cues like that can help us remember some of the rules. So for example, like a 50-degree angle and a 40-degree angle. These are complementary because they add up to 90. And we could say similarly, a 100-degree angle and an 80-degree angle are supplementary. And knowing these rules are going to help us find missing angles. So here's what I was talking about before, a linear pair. A linear pair are angles that are on a straight line, that word linear, and they always add up to 180 degrees. Because we know a straight angle is 180 degrees. Remember, we learned that last class together. So this is on a straight line. We know that these two angles add up to 180. So we can set up a little algebra equation and solve for B. So this takes us back to last year. We'll subtract 50 from both sides, and angle B is 130 degrees. Now, likely with this example, you probably didn't have to set up this equation, and that's totally fine. You maybe even did this in your head, and just said 180 minus 50. Or maybe you grabbed your calculator, and that's totally fine. Here's another pair of angles on a straight line. Now this one, we have a little more complicated expression, so we might want to write it out. 3x plus 18 plus 93 equals 180. So we're going to solve for x. So first, let's combine like terms. 93 plus 18, 111. I did that in my head, sort of. 8 plus 3 is 11. 9 plus 1 plus 1. There we go. And then we're going to subtract 111 from both sides. And you get 3x equals 169. And then divide by 3. I don't have my calculator handy, so let's do this old school. You guys can totally grab your calculator though. 3 goes into 16 5 times. Ooh, does this not go evenly? Let's grab our calculator. No, it does not go in evenly. 3 goes into 19 6 times. Oops, 6 times. And you're left with one left over. So this is also 56.3. And that's totally fine to have decimals, just wasn't quite expecting it. All right, parallel lines. So parallel lines are lines that have the exact same slope. We talked about these last year in algebra as well. They will never cross, ever, because they have that same slope. One way we can note parallel lines is by using arrows like this, and they have the same matching arrows, or sometimes you'll see like little triangles drawn, solid triangles. If you have more than one pair of parallel lines in a diagram, then they'll oftentimes use 2 arrows because they want to make sure that you're matching up the lines that are parallel together. So they're saying these two have the same slope, and we're saying these two have the same slope. And our last topic from last class are perpendicular lines. These always form 90-degree angles. And it looks like 90 degrees, doesn't it? But we know that unless we're told it's 90 degrees or we're told they're perpendicular, we don't really know. And they have opposite reciprocal slopes. And let's remember what that means. For example, line 1, remember m is slope, maybe it's 1/2. And the perpendicular slope would be, we flip it 2/1 and make it negative. This is our symbol for perpendicular. We don't really have one for parallel. That's funny, isn't it? There is a symbol for perpendicular, but not parallel. All right, now we're going to get into our transformations. This is, again, corresponding to 110 through 111 and 114. We're going to get to 1.13 later this week, so don't worry, I didn't forget about it. Go much further. I wanted to take you guys back to this problem. I was thinking, there is no way I can put a problem up there where I'm going to have 56 1/3 degree measure. So I was like, let me go back and look. And, we're all human, and this is great error analysis for us. And hopefully you guys saw, and maybe you were screaming at my video and already sending me an email going, Miss Winslow, I see what you did. See right here? 180 minus 111. That is not 169. 180 minus 111 is just 69. Right? Divided by 3. That does go in evenly. And we get 23. So x is 23. And the other way we could have totally checked our work as well is by plugging that x value in here and seeing, do they really add up to 180 degrees? And if we put in that 56.3 that we got, it would not have worked. So this is a really good lesson that we all learned together. Good error analysis. Double check your work. If we plug in 23, we're going to get, let's see, 9. So that's 69 plus 18. 69 plus 18 is 87. So we're saying this is 87 degrees. Now to continue checking, we need to make sure that 87 plus 93 does in fact equal 180. 87 plus 93. And sure enough, it does. So we were able to double check and confirm that our answer of 23 is correct. Have you guys heard of M.C. Escher? M.C. Escher. I'm guessing you probably have. And M.C. Escher uses transformations in his artwork a lot. So here's an example where they took a shape and they translated it. It almost looks like the bird is flying. And then when you do that, you end up with this negative space here. Here's a bunch of them. Imagine that space to be white. And then the whole idea is you turn it into something else. So in this one, the artist turned it into a fish. It's pretty cool. So we do see art and math combine themselves quite a lot. This is just one example. There are a few different kinds of transformations, and this is where you're going to start taking your notes. Transformations describe how figures relate to each other after going through some kind of change. And these are the changes that they can go through. There can be a translation, a reflection, rotation, or an enlargement. So a translation, and we're going to talk about these a lot more on the next pages, but you can see in this diagram, you're just taking the shape and moving it up, down, left, right, typically. A reflection is exactly what you think it is. When you think of a reflection in the mirror, right, you're kind of seeing the mirrored image of something. Rotation is turning a figure around some point. And then an enlargement is also known as a dilation. Let me write that here for you. And we're going to talk about that on the next slide, on the next slides. But the shape can get bigger or smaller. It can shrink, or like this little shape is shrinking, or it can expand. So these are the 4 types of transformations. Here's just a little example I found on Google. Someone took this old school Little Tikes car and they transformed it. So this is a funny example of transformation. Of course, it's not exactly mathematically accurate because, they did some painting and such. But if we think about this as just shifting to the right, that would be an example of a translation. I definitely like the second car better. It's very jazzy. I like the cherry on top. It's cute. All right, so let's keep filling out our notes here. There are a few words we want to sort of go over. The first one is the image. So the image is actually the figure, whatever it might be. In this example, we're looking at some capital A's, but it's the figure after the transformation. It's the figure after the transformation. Oh, it's right there. And the pre-image is the original figure. And we have some special notation for this, of course, always, right? There's always going to be some way to shorthand write this. So here they're telling us that the blue A is the original figure. It's the pre-image. So to label this, we're going to use capital letters to label points. And I'm just going to do ABC as an example, sort of the three corners. You can see there's a lot more points in that shape, right? I'm just going to do ABC as example. So this would be B, this would be A, and this would be C. Whoops. I got that flipped. Hold on. Because they're rotating it. So this would be C and this would be A. That doesn't much matter for what I'm trying to show you on this example, but there we go. So with the rotated image, that's the image after the transformation. So you want to mark that to be differently. And we use these little tick marks, and they're called primes. So we say A prime, B prime, C prime. So the original or the pre-image, pre meaning before, right? So before the transformation, it's called the pre-image. We use capital letters, A, B, C. The image, which is going to be after the transformation, we use the prime marks. So you can show that's the point that's different. And we call these little tick marks prime. So we say A prime, B prime, C prime. And it's just a way to say, okay, it's the same point because it's the same shape, but something's happened to it. Some change has happened. So it's the new point. So we have some special transformations. They're called isometric transformations. They're very special. It's a transformation that preserves the size and the shape. So it's not going to get bigger or smaller. It's going to stay the same size. It preserves the size, and it's going to stay the same shape. So it's not going to, shrink and turn into something else. So which of the following transformations do you think is isometric? Which one of these will never change the size and never change the shape? Well, a compression, that's going to change the size, right? It's going to make it smaller. So it can't be that. A dilation is going to also change the size and make it bigger. Compression would also change the shape. That's definitely not it. So yes, it is just a reflection. A reflection is taking the exact same shape and just flipping it. So it will stay the same size and it will stay the same shape with a reflection. So there are three different isometries. We have reflections that we just talked about. Rotations. So again, if you just take a shape and turn it around something, you're not changing the size and you're not changing the shape. And a translation. So if you were to take a shape and just pick it up and move it to the right, you have not changed anything about the size or shape. So size and shape stay the same for an isometry. For isometric transformations. So if a transformation is isometric, what does that mean about the shape? And it's really powerful and it's really helpful. It means that the shapes are congruent. Whoops, let me get my pen back. If a transformation is isometric, it means that the shapes are similar. No, hold on, let me delete this. We'll get to similar later. They're congruent. Remember, congruent means the same value, like the same length, but they're not the exact same shape, right? Because we have a blue one and a red one. But you can see just by reflecting it, it did not change the side lengths at all. AC is 5, A prime, C prime is still 5. And it did not change the angle measures. You could definitely get a, oh boy, wish you guys were here, protractor. Remember, I have issues remembering whether it's a protractor or a compass. I think it's a protractor. Yes. It's just the issue I have. We talked about this last class. You could get a protractor and measure those angles, but we did not stretch or shrink the shape at all. So it did not change the angle measured. So the shapes are congruent, which means whatever angle C is congruent to angle C prime. Angle A is congruent to A prime, and angle B is congruent to B prime. Side note, this is actually a super special triangle. It's called a special right triangle. And we're going to get to this in second semester. It's a special one. It's a Pythagorean triple. It's a 3, 4, 5. Very special triangle. But the point here is if the transformation is isometric, then the shapes are congruent. So there are 4 types of transformations. Remember, we talked about this in the very beginning. So the first one we're going to look at a little bit more is a reflection. So you can see here, this example, that the image and the pre-image are reflecting over this line K. So sometimes people have a tricky time sort of envisioning transformations because it's kind of a 3-dimensional thing happening on a 2-dimensional surface. So if you need to, grab something in front of you, like a pencil, and flip it over, or a piece of paper and flip it over. You'll see, I just did that, how a reflection works. We think of that as a flip. The other thing to note here is this word equal that they're pointing out, is that the distance from the points are going to be the same. Equal distance from whatever line you're reflecting it over. So we're reflecting over the line K here. So the distance from K to A, let's call it 5, will be the same from K to A prime. I'm just making up 5. Same from B to B prime. From this point K, these distances are going to be equal. I'll call it 6. And same thing here, maybe 1. So that's the special sort of outcome of reflecting over a line. Is the distances from the line to the points, from the image to the pre-image, are going to be equal. So we can write here, equal distance from the line of reflection. Here the line of reflection is line K. All right, let's look at the next one. So we have a rotation. There are so many different angles you could rotate about a shape. So in this class, we're mostly going to be looking at 90 degrees, 180 degrees, and 270 degrees. They're all kind of multiples of 90. And we have some special rules for doing that. I'm going to write them here. And we'll talk about them a little bit more, but I want you to have them on this slide. You take the XY point, and all you do is you flip it and make the Y negative. And again, we'll look at some examples. We can look at this one. And then 180, we're going to take the XY point, and we're just going to make them both negative. And that makes sense if you think about it. If 0 degrees was here, 90 degrees is here, 180 degrees here. To be 180, excuse me, well, it kind of depends where your shape starts. So we'll get to the examples and I'll show you that. 270, we are going to flip the coordinate point and make the x negative. So these are kind of the rules that you guys can remember that match with these rotations. It makes it super easy. All right, next is a translation. This is the slide. This is where you're just moving it up, down, left, or right. Up, down, left, or right. And when you're doing that, all you're doing is you're adding or subtracting from the x and the y. This is sort of the most traditional transformation. You know, we take this A point and we moved it, what, down 2 So we subtracted, down 2 and over 1, 2, 3, 4, 5, 6, and over 6. So with a translation, you're just moving up, down, and left and right. A dilation, I always think of when I go to the eye doctor. Maybe we've talked about this before. Let's see if I can draw an eyeball. You go to the eye doctor and you get your eyes dilated for an eye exam. So when they put that stuff in your eyeball, your pupil gets huge. It becomes almost the size of your iris. Whoop. So it becomes dilated. That's how you remember this transformation, but dilation also means shrinking. So something can expand, it can get bigger, or it can shrink. So in this example, A is A, B, and C, that is the pre-image, right? Because it's just a regular A, B, and C. So pre-image is ABC, triangle ABC. And the image, the shape after the transformation is A prime, B prime, C prime. So how did the green triangle change? It got bigger, right? It expanded. By how much? And we're going to talk about that. That factor is called a scale factor. That's another word I want you guys to add to this slide. And that is how much something shrinks or expands. So we get to put a value to it, which is nice because that's going to help us perform the transformation. So one little tidbit, let's put it up here. It will be expanding if the scale factor is bigger than 1, and it will be shrinking if the scale factor is less than 1. Two kind of values to keep in mind there. All right, so here's an example. Lily slides a book 6 inches to the right. What transformation could this be? So sliding to the right, that is a translation. You're just taking it and you're pushing it over 6 units or 6 inches. Aw, I feel like I've shared this one with you before, maybe not. Why is the obtuse triangle always upset? Because it's never right. Oh, sad. All right, so let's get into some of these transformations, and we're going to use algebra to describe them. And algebra is one of my most favorite subjects, which also makes me really like geometry, because geometry is technically like 10% geometry and the rest is algebra. Like once you set up the geometry stuff, the algebra just falls through. So let's do a quick recap of the coordinate plane. So on your notes, you have a coordinate plane there. You guys remember the quadrants? This is quadrant 1. This is quadrant 2. We go in a counterclockwise direction to label them. Quadrant 3 and quadrant 4. In quadrant 1, well, first, let's point out this dot right here. This is the origin. Right in the center is the origin. And then you have the x-axis and the y-axis. Those are labeled. One way I remember that the vertical axis is the y-axis, this is going to seem nuts, but it always works. Because when you start to draw a y, you're like, oh, look at my long y. That's that vertical axis. So sometimes that helps me recall that the y, back in the day when I was a student, I tried to come up with ways for me to remember things like this, because sometimes people mix up the x and y a lot. That's like a common error. So the y-axis is the vertical axis. And now let's review coordinate points. So in a two-dimensional space like this, our coordinate points are x, y. And the nice thing is it's alphabetical, right? X comes before y, just like it does in a regular coordinate point. And you're always going to graph x before you graph y. So let's try some examples. Let's graph -1, 2. So we're going to always start at the origin. You always start at the origin. I'm going to start here, and we're going to go in the x direction first. So I'll go -1 to the left, and then up 2. There's our coordinate point. Let's call it A. So we can label that. Okay, let's try another one. What if we did -3, -5? So we're going to start at the origin. And remember, you go in the x direction first. So this is x, and this is y. So we're going to go to the left 3 and down 5. We can call this point B. How about if we kind of go in reverse? Like, what if I put a point here and I say, hey, what is the coordinate point of this one? Let's call it C. So you do it the same way. To get the actual values, we'll start at the origin and we'll count over in the x direction first. 1, 2, 3, 4, 5. So x is 5 and y is 5. That's it. Let's do one more of those. How about here? We start at 0, 0, and we'll go over 3 and down 3. I did not make that up on purpose. All right, so that was a nice review of our coordinate plane. Actually, I was going to do that on this slide, those examples. So we'll go ahead and skip this one. So which quadrant is -3 and -5 in? Remember, we're going to start at the origin, go over 3 and down 5. It is in quadrant 3. Oh, I didn't show you guys that we can sometimes label these using Roman numerals. So sometimes you'll see 1, 2, 3, and 4. Or I don't know why, I just kind of do, whoops. I just do Q1, Q2, Q3. But you might also see Roman numerals. So that's a good review of those. You might not remember that IV is 4. So it is in quadrant 3. Here we go. Sometimes people like to label this as well, like the signs. So quadrant 1 is positive, positive. Quadrant 2 is negative, positive. And that's because the x value is negative, right? If we start at 0, 0, all the x's are negative and all the y's are positive. Quadrant 3 is negative, negative. And quadrant 4 is positive, negative. So you can see here we have a negative, negative. So sometimes people instantly think, oh, that's quadrant 3, without having to actually plot the point. So let's talk about reflection across the x-axis. So I'm going to make a shape. Let's put some points in here. We're going to call this triangle ABC. And B is coordinate point 4, -2. C is 4, -4. And A is 2, -4. So remember, the rule for reflection across the x-axis is you take the x and y coordinate point and you make the y negative. So you guys see this arrow here, and that's kind of the word that means transform. I'm sorry, not the word, it's the symbol that means, okay, go ahead and do the transformation. So take the x, y, and the output changes to x, -y. So we're just going to take each of these coordinate points. I'm going to write them over here so we can go ahead and perform the transformation and make the y negative. So the image is going to be A prime. And instead of -4, we're going to have a +4. The image of B is B prime. And instead of -2, we'll have a +2. And the image of C is C prime. And instead of -4, we're going to have a +4. So let's plot the new shape on the coordinate plane and see what it looks like. So 2, positive 4 is A prime, and 4, positive 2 is B prime, and 4, positive 4 is C prime. There's our triangle. You can see, I'm going to grab my highlighter. Here's the x-axis. We took this entire red shape and plopped it over that x-axis, so it reflected upwards. It went from quadrant 4 up to quadrant 1. And again, it's kind of hard to see that three-dimensional process happening, but hopefully you can imagine it. You know, the A was down here, so now it's flipped up top, and similarly with the B and the C. So remember, whoops, this is called the pre-image. It's the shape before anything has happened to it, and this is called the image. Let's do another one. Let's do across the y-axis. So remember, the rule to reflect across the y is to make the x negative. So let's put something over here. Let's do, I don't know, how about a rectangle? That sounds good. Some people can do reflections visually, like they would see this shape and they would be able to just plop it over the y-axis and sort of draw the new one. And I bet you could too. Look, you're like, okay. Oh wait, that's 2. Look, I already messed up. That B and C point, they are 2 units away from the y-axis. So you can make the new points 2 units away on the other side. Remember when we talked about the definition of a reflection, it's the same distance away from that line. So the new point would be here. Let's try it this way and then check it with the rule. C is 2 units away, so C prime would be 2 units away. A is 5 units away from that line of reflection. So let's make A prime 5 units this way. And similarly, D prime is going here. So let's try it with the points. B is negative 2, 4. Here, I'm going to label it over here. A is negative 5, 4. B is negative 2, 4. C is negative 2, 2. And D is negative 5, 2. This is why we reviewed how to find points, right? Because we're going to use it a lot. Let's just make the x negative. So 5, 4, 2, 4, 2, 2, and 5, 2. And let's check our work. Sure enough, look, over 5 up 4, there's point A prime. Over 2 up 4, there's B prime. 2, 2 is C prime, and 5, 2 is D prime. Yay! It worked. So again, this is the cool thing about math, is there's usually more than one way to solve a problem. You can do it visually, or you can do it using the rule. Let's try reflecting it over the line y equals x. So the line y equals x, I don't think this is a rule that we've talked about yet, but I'll show you guys here. All you do is you switch the coordinate point. So the line y equals x actually goes right through the origin. Here is the line y equals x. If you recall that from Algebra 1. If not, you can absolutely graph that line on your Desmos calculator. Just type y equals x, and this is the line that will show up. So let's put something down here in this quadrant. This little tiny rectangle. Okay, let me expand it since okay. A, B, C, D. So we'll do it. I have a very hard time doing these reflections visually with this line because you're taking this and you're moving it over the line diagonally. So if you think of folding a paper along a diagonal and reflecting that shape over that diagonal. So I like the rule here. A is 3, -2, +3. B is 4, -2. Why do I keep getting a little tiny mark there? Do you guys see that? Okay. C is 4, -5. And D is 3, -5. So to get the image A prime, let's switch those coordinate points. B prime, we're going to switch them. We're going to switch the X and Y. All right, now let's plot the points and see what happens. So -2, 3 is A prime. -2, 4 is B prime. -5, 4 is C prime. And -5, 3 is D prime. There it is. This is why I have a hard time, because not only did it totally change where it is, it even like changed its direction. Like it's not vertical anymore, it's horizontal. Totally flipped, and it kind of rotated in a sense. Like it went to the first quadrant and then the second, or the third and then the second. So we're going to flip those X and Y points. The last one we're going to look at is 180-degree rotation. And for this one, it's a very common one you'll see a lot, so that's why I wanted to go over it, is you make each of the coordinate points negative. So let's put something down here. I don't think we've had anything down here. We can do a triangle. Label it A, B, C. Rotations are also, I think, challenging to do visually, but if you're up for it, you guys go right ahead. A is -5, -3. B is -5, -5. And C is -2, -5. So let's find the image and just make these coordinate points the opposite sign. So this negative means to make it opposite. So instead of -5, we're going to have 5 and 3. 5 and 5, 2 and 5. So let's plot the new points. 5, 3 is A prime. 5, 5 is B prime. And 2, 5 is C prime. See, I could definitely not do this visually. Some people can, though. I admire them. So we rotated that 180 degrees. Oh, these were the rules we talked about earlier under rotation. One thing I want to point out is these are counterclockwise. So counterclockwise, we took this shape and we rotated it this way, 180 degrees. Each of these quadrants is 90 degrees, so that makes sense, right? It went 90 this way and then another 90 to get up here. So that's 180. So let's do some practice. These are some actual SOL questions from previously released tests that I thought we could go over. Triangle ABC is reflected across the x-axis and then reflected across the y-axis to create a new triangle. What are the coordinates of A prime? So we really only have to worry about A here. A is 1, 4. Now again, if you're visual, you can do this, but I'm going to use the rules. So we talked about the rule for a reflection across the x. Remember, that is x negative y. So first, I'm going to take coordinate point A, and I'm going to do this to it. I'm going to make the y negative. So that's our first transformation, the x-axis, done. Then across the y-axis. So remember the y-axis rule is negative xy. So I'm going to take this new point that I already transformed, and do it again. I'm going to make the x negative. Negative 1, positive 4. There it is. It is D. And if you wanted to, you could definitely do that with all the points and kind of replot it to pick or to make sure it makes sense. Those are the two rules in action. So sometimes you'll see transformations combined. All right, rectangle ABCD prime is the image of rectangle ABCD. After which of the following translations? So they're telling you it's a translation. So remember, a translation just goes up, down, left, or right. Up, down, left, or right. And we kind of have to figure out what it did. So I honestly feel like the easiest way to do that is just to focus on one point. Like I'm just going to look at A and see how did A change. Well, here's the new A. Right, so it went 1, 2, 3, 4, down 4 units, and 1, 2, 3, 4, 5, 6 to the right 6 units. So let's figure out which one of those matches. A says 4 units in the positive x direction. Well, we went 4 units down. Going down is going along the y-axis. When you go up and down, you're going along the y-axis. So that's in the y direction. We went down, we went negative 4 in the y direction. So let's find the one that says 4 units in the negative y direction. So it's not this. It's not this one. That's a positive y. Negative x. Ooh, here it is. A and C are the ones that say negative y direction, but we went 4 units in the negative y and 6 units in the positive x. Remember, going horizontally is the x direction. So sometimes part of this is also using process of elimination. Here's number 3. Transformation. They give you the transformation rule. They say, okay, add 2 to every x value and subtract 3 to every y. They want you to apply it to this triangle. What are the coordinates of B prime? So let's look at B. B is, negative 2, 1. So all we have to do is apply this transformation, this rule. This is one way you'll see the rules written. So I'm just going to add 2 to my x value, and I'm going to subtract 3 from my y value. Negative 2 plus 2 is 0. 1 minus 3 is negative 2. That's the new B prime. I just applied the rule. That's it. Here, let's try another one real quick. Let's do C. So C is, this is negative 3. Negative 3, comma 4. So let's apply the rule to point C to get C prime. We're going to add 2. And you don't have to write it out like this if you don't want to. I'm really just doing that so you guys can see the math. And subtract 3. So C prime is negative 1, comma 1. That's it. Here's our last one. Which mapping describes the transformation of pre-image ABCD? Remember, the pre-image is the shape we started with. That's this one. And it transformed to the new shape. So this time they want you to write the rule. So remember, in this example, they gave us the rule. This example, they gave us the transformation, and they want us to write the rule. So we have to figure out, how did these points move? And I, again, think the easiest way is just to focus on one point and get to the get to the image in the pre-image. So how did point A change? We went down two, and 1, 2, 3, over 3. So when we say down, it means we subtracted 2 in the y direction, right? That's up and down. So that's going to change our y values. So we're going to do y minus 2. And then we went to the left 3. Remember, going to the left, you're going in the negative direction on that number line. So we're going to subtract 3 from all the x values. Remember, that horizontal x-axis is the one that goes left and right. So x minus 3. So you're kind of just working backwards. That's it, you guys. Here's some examples of sort of grids and transformations in real life. Please tell me you know what Pac-Man is. Please, please, please. This is Pac-Man. I'm sure you do. You guys are, a lot of you like video games. I used to play Pac-Man in like the old school arcades. So much fun. So the people who actually programmed Pac-Man used these transformation rules, literally, in the programming to make the shape go up, down, left, right. Isn't that cool? And the same with GPS. This is a map of the global positioning system. Uses some aspects of this. And this is just another map showing the GPS system here. Thank you guys for sticking with me, and I'm here if you need anything via email, and I hope that you guys have a great week.